Hey guys, Miss Gosling here. In this video, you are going to learn about conservation of energy. By the end of the video, you'll be able to solve problems involving the law of conservation of energy. So let's go ahead and get started. And of course, the best way to start is by talking about what the law of conservation of energy actually says. And the law of conservation of energy says that energy cannot be created or destroyed, only changed. So what this means is I can't create gravitational potential energy out of nowhere, but I can use the chemical energy in my arm and the kinetic energy in my arm moving to lift a pencil up above the ground before dropping it, therefore converting it into gravitational potential energy. Now, one thing I do want to mention is that just because energy, the total energy in the universe is going to stay constant, doesn't mean that the energy in a system will stay constant. So, for example, if I am running electricity through a circuit, some of that electrical energy is going to be lost to heat and light. So it's being transferred into another form of energy, but it's not a useful form of energy. So one way that we can differentiate between systems where energy is conserved and systems where it's not is by differentiating between closed and open systems. And in a closed system, the total energy will stay constant. That is to say, no energy in a closed system is going to be lost to heat, light, or other forms, or things like deformation. Whereas in an open system, heat and light and all other kinds of things are going to be are going to be ways in which our energy is transformed. So let's take a look at an example of a closed system. Now, in real life, a roller coaster is an open system because some energy is lost to heat through friction, as well as through some potentially slight deformation, which is a little less easy to see. But for example, if any single tiny bits of wood are shaved off of a roller coaster, that's an example of deformation. Anyhow, if we are assuming that our roller coaster is a closed system, what that means is that the total energy here, I'm going to call that E1, is equal to total energy down here at E2, and is equal to the total energy at E3 in the middle, and at E4 over on the left-hand side. Now, some of that energy is going to be kinetic, and some of that energy is going to be potential, but the total energy, K plus U, is going to be constant. So if we're looking at our first hill, you can see I split up my energy between K and U. At my higher hill, most likely all of my energy here is going to be potential, specifically gravitational potential energy. But my K plus U, my total energy, is going to be constant. Similarly, over at E2, my bottom point, most likely all my energy will be kinetic, so I'll have no potential energy, but my total energy is going to again be constant. And then at E3, just like E4, my kinetic energy and potential energy are going to be about equal because I'm about halfway down. But again, the same total energy. So again, the key takeaway here is the type of energy that we have is going to vary, but when I add all my energies together, it is going to stay the same. So let's look at an example of this. And this is going to be putting our roller coaster problem into words. A cart of mass 100 kilograms holds 10 people, each with an average mass of 50 kilograms. If the cart is at rest at the top of a 15-meter roller coaster hill, how fast will the cart be traveling when it hits the end of the hill? So when it's at, I'm going to cross off end, I'm going to go ahead and write bottom instead because I think that might be a little bit more clear where we are. So let's go ahead and draw a picture of what this looks like. So here is my roller coaster, like so. I'm at the top and I'm at the bottom. So at the top, my height is 15 meters. And the mass of my cart is going to be 100 plus 10 times 50. Or 600 kilograms. At the bottom of the hill, my height is going to be 0 meters, and my mass is still going to be 600 kilograms, since we presumably have not lost any of our riders on this hill. So at the beginning of my hill, the only kind of energy that I'm going to have is my potential energy. So actually, let me go ahead. I'm going to back up because I've listed my givens. I have not listed my unknown, but my unknown is my speed at the bottom of the hill. So let me go ahead and move into that equation section and walk through this a little more slowly. So I know that my energy at the beginning, which I'm going to call E1 or E initial, is equal to my energy at the end, or E final. Now at the beginning of my hill, I am at rest, but I'm 15 meters up. So that means that all of my energy is gravitational potential, or UG. At the end of the hill, my height is 0, but I'm moving. So all of my energy is going to be kinetic. So that means that my mass times G times my height at the beginning is equal to 1/2 times my mass times my speed at the end squared. Now, what I'm going to do is I'm going to go ahead and manipulate my equation so that I can get my speed at the end by itself, since that's what I'm trying to find. So to do that, I'm going to need to multiply both sides by 2 to get rid of that 1/2. And I'm going to need to divide by m so that v is by itself. And I need to take that square root. Now, one thing you'll notice is that when I divide by m, that's going to cancel out the mass on my right side of the equation. It's also going to cancel out the mass on my left side. So if my mass doesn't change, then it's going to cancel out, which is really nice. Now, this is only true for gravitational to kinetic, not for elastic energy, potential energy to kinetic energy, because there's no mass in my elastic potential energy. But this is still really good to know for our gravitational problems, which are the more common problem that you'll see. So solving this out, what I get is that V final is equal to the square root of 2 times G times my height at the beginning. So let's go ahead, now that I've done all that fun manipulation where you can see again why manipulation is so useful, why solving for V is so useful before I plug in numbers is so useful. Now that I've done that, I can sub and solve. So I know that V final is equal to the square root of 2 times G times H, or the square root of 2 times 9.8 times 15. Plugging that into my calculator, I get that my final velocity is 294 meters per second. And there you go. Now, I do want to back up for a moment and talk through the process that I recommend using for solving conservation of energy problems. So step 1 is going to be draw a picture for the beginning and the end of the problem. And under the pictures or on the pictures, list your givens. So I don't want you just drawing a picture of whatever's happening, and I don't actually care how nice your picture looks. What I care about is how accurate is it? Is it labeled? Do you have your units listed there? Do you have your givens listed? Do you have your unknown listed? Next, I want to determine E total for both sides. And specifically, I want to know what's the combination of U, UG, UE, and K for my beginning and my end of my problem. And then finally, I'm ready to solve for my unknown once I've expanded, once I've done all my canceling out, all that fun stuff. I'm going to use that example to solve a similar example problem to my first. So this time, a cart of mass 100 kilograms, still holding 10 people with an average mass of 50 kilograms, is going to rest at the top of a 15-meter roller coaster hill. But this time, I want to know how fast the car will be traveling halfway down the hill. So let's go ahead and draw out that problem. So here is the top of our hill, and that is going to be 15 meters up. And at the top, my roller coaster is still going to have, my cart is still going to have a total mass of 600 kilograms. And my velocity is still going to be 0. Now, halfway down the hill, my height is going to be 15 over 2, or 7.5 meters. My mass is still going to be 600 kilograms, and my velocity is something. So looking at my picture, I can see that at the beginning, I only have gravitational potential energy since my velocity is 0. Halfway down the hill, I still have some gravitational potential energy, but I also have some kinetic energy. So some of my potential energy has been converted into kinetic energy. And that means that I'm ready to write my equation and then move towards subbing and solving. So I know that E at the beginning, so E initial, is equal to E at the end of my problem, which is halfway down the hill, E final. So notice that E final is not the end of the story. So it's not the end of the roller coaster, it's the end of my problem. So the second place in my problem. So at the beginning of my story, I only have gravitational potential energy, whereas at the end, I have a mix of gravitational and kinetic. And I'm going to go ahead and call them gravitational initial, and gravitational final and kinetic final, just to differentiate between those two UGs. So expanding that out one bit more, I know that my gravitational potential energy is mg times the height at the beginning. And that's going to equal mg times my height at the end of my story, plus 1/2 times m times the velocity at the end of the story squared. Now, looking here, I can see I have an m in each of my terms. So that means if I were to divide by m, everything would all of my m's would cancel. And that is going to then simplify my equation to GH initial is equal to GH final plus 1/2 v squared. Next, I want to subtract GH final from each side. And so that is going to give me, and I'm going to move that up here, GH initial minus GH final is equal to 1/2 v squared. Next, I'll multiply by 2 and then take the square root. So 2 times GH initial minus GH final, and again, you'll notice those parentheses there because I have to multiply both of my terms on the left side of my equation by 2 since I'm multiplying the whole thing by 2. And the square root of that whole thing is what I'm going to do. And that is going to equal my final velocity. So now I'm ready to sub and solve. And before I do that, I do want to mention, if you were to stop at this step and put your numbers in then, that would also make sense. However, you are going to want to make sure you check for what can cancel out before you add in numbers. So moving back, let's sub and solve. V final is equal to the square root of 2 times G, 9.8, times my initial height, which is 15, minus 9.8 times 7.5. Now, notice I could have taken the G out here, and like so. I chose not to do that because I think it's a little unnecessary, but just one less thing to put in your calculator if that is something you are interested in. So I've substituted my numbers, and now all that's left to do is stick that in my calculator. And when I do so, I will find that my final velocity is 12 meters per second. And there you go. Now let's solve one last problem. So a rubber, and this one's a little more complex than our first two. So a rubber band of mass 10 grams and spring constant 1.0 newtons per kilogram, or newtons per meter, excuse me, is held at arm height, approximately 1.3 meters, and extended 10 centimeters. What will its velocity be when it hits the ground? So this time, what I'm going to do is I'm going to draw out my stretched rubber band here and my loose rubber band on the ground here. So initially, my rubber band is stretched to x equals 0.1 meters, and it has a height of 1.3 meters. Now, I know the spring constant K for that rubber band is 1.0 newtons per kilogram. And I know that the mass of my rubber band is 10 grams or 0.01 kilograms. Now, on the ground, my height is 0 meters. My x is 0 meters. K doesn't matter, but my mass is 0.1 kilograms, or 0.01 kilograms, excuse me, and I am trying to find my speed, since that is what the question is asking me for. That looks like a 2, not a question mark, excuse me there. So again, what I've done is I've labeled everything from my problem. So I've figured out this is from the beginning, that is for both, this is for both, this is for both. The height only exists at the beginning, as does that stretch. And so I'm able to break my variables up between the beginning and the end of my problem. And now I'm ready to write out my equation. So I know, of course, that the law of conservation of energy says that my initial energy is equal to my final energy. So let's go ahead and expand this out. So at the beginning, we have gravitational potential energy. We have elastic potential energy from the stretch of the rubber band, and we don't have any kinetic energy. But at the end, all of our potential energy has been converted into kinetic energy. So let's expand that out a little more. So I know that mgh in the beginning plus 1/2 kx squared, again at the beginning, is equal to 1/2 mv squared at the end. Now you'll notice here that I can't do any canceling, but what I can do is semi-simplify by getting v by itself. So I'm going to start by dividing both sides by m, and my m's are going to cancel at least for some of this. So that gives me ghi is equal to 1/2 k over m x initial squared. And that is going to equal, x initial squared, and that's going to equal 1/2 times v final squared. Then when I multiply both sides by 2, what I'll get is that 2g times my initial height plus k over m times x initial squared, since my 2 is going to cancel out my 1/2. And that's going to equal v final. And when we take the square root, we don't have to continue writing that little squared. So now I'm ready to sub and solve. And one thing I want to mention as I'm writing out sub and solve, again, you do not have to do these steps, but sometimes they make your life a little bit easier. So you don't have to simplify before you plug in numbers, but often I found that it reduces error. Anyhow, plugging in my numbers, what I'll find is that v final is equal to the square root of 2 times 9.8 times my initial height of 1.3 meters plus k, or 1, over m, which is 0.01 kilograms, times 0.1 squared. And now I'm ready to plug that all into my calculator. And when I will do so, I will get that v final is equal to approximately 5 meters per second. And there you have it, guys. That is going to be my solution to a slightly more complicated conservation energy problem. So let's go ahead and talk takeaways. First of all, energy is conserved, specifically within a closed system. And second, we can use the law of conservation of energy to solve problems. Again, for closed systems, which we will assume that our systems are closed unless the problem states otherwise. So guys, it is now your turn to try solving problems on your own. I know this sounds complicated, but I also know that you guys are very much capable of doing it. So go ahead and give it a try. Best of luck and happy solving.